All right, this will hopefully be the last video for section one. I know there's 6 or so videos of this one so far, but the remaining sections won't have as many videos. It's just a really big one. So the last thing that we need to talk about here in section one is to find volumes of solids of revolution whenever your area that you're going to be revolving is not bordering your axis of rotation. So here if we had these two functions, big R of x and little r of x, and it created the area in between the two functions from a to b in the xy plane, if I were to take this area and then revolve that around the x-axis, there would be this gap here. So this would be the shape that it ended up making, this kind of, I don't know, funnel-looking shape. And if we want to find the volume of this, we're still going to use our disk method, but we're going to have to do two separate disk methods and then subtract them. We're going to do the disk method of the outside function and find that total volume, and then subtract away the disk method of the inside function, that part of the volume that we wouldn't care about. That's the hole here that you see inside of our funnel. So just to kind of write it all out as just a generic formula, it's here. This is what we call the washer method. We call this the washer method because you make these little washers. It's just a disk with a hole in it. So to find the volume, it's the integral from a to b of pi, the outside radius as a function of x squared minus the inside radius function of x squared. Again, all that really is this two different disk methods of the outside radius minus the inside radius. But this formula you can think of for the washer method. And you want to use the washer method when the area is not bordering the axis of rotation, where you have that gap. All right, we're going to do an example together here. We're going to do this one, example 9. So the region bounded by the curve y equals x squared plus 1 and y equals negative x plus 3 is revolved about the x-axis to generate a solid. Find the volume of that solid. All right, so first thing we want to do is we want to find the region that we're going to be revolving. So that's going to be using these two functions, x squared plus 1 and negative x plus 3. So just to kind of write them out. And we want to graph these two things. All right, so x squared plus 1, that's just going to be the parabola that's moved up by 1. So it's going to have the origin here at 1. It's just a normal parabola. Great. And then negative x plus 3, that one's going to be a line. It's going to have a slope of negative 1, and it's going to have a y-intercept at positive 3. So it intersects here, and then the slope of negative 1 is going to look something like that. Which means that my region is this kind of half crescent shaped region in between the two functions. And we're going to take this, remember, and we're revolving that around the x-axis here. So this way. Okay. What we want to do is we want to use the washer method for this because the region that we are revolving is not bordering the axis of rotation. So with the washer method, just to write the formula out again, that's going to be the area from a to b. We'll come up with the a and the b here in a second. The pi is on the outside, and then it's the outside radius, capital R of x quantity squared, minus the inside radius, little r of x quantity squared, then that whole thing dx. So we need to come up with the outside radius and the inside radius as a function of x. Almost always is going to be your two functions. You just have to be careful about which one is which. The big R, the outside radius, is always going to be the function that is furthest away from the axis of rotation. So if my axis of rotation here is the x-axis, then the top part of my region is this straight line here. So that means that is going to be my outside radius. The distance from the axis of rotation to the top part, the furthest value away, is going to be this negative x plus 3. So that's going to go here for my outside radius. Oh, oops, pulled my pin button down. The inside radius is going to be the shortest radius, which is going to be from the x-axis to the parabola x squared plus 1. So x squared plus 1 goes here. Other than that, we have to figure out the limits. That means that we need to figure out what these two intersection points are. Oops, didn't mean to erase that. So this intersection point here and then this intersection point here. A couple of different ways you could do this. You could just use your calculator and graph these two things, then find the intersection points. You could set these two things equal to each other and figure out what they have to be, or you can just guess and check. Like it kind of looks like if I plug, let's see, -2 into these two things, then it's going to work, right? Because -2, making it negative is +2, plus 3 is 5. -2 into here squared is 4, plus 1, which is 5. So that has to be at -2 on the x-axis. And then just try things for this one as well. What could it be? 1, it looks like. My graph is like way off. Sorry about that. It's not very symmetric. But it looks like 1 for this one. Okay, cool. So we're going from -2 to +1 here on the x-axis. So just to do the integral real quick. Integral -2 to 1 of pi. And then it's the outside radius squared. So that -x plus 3 quantity squared minus the inside radius x squared plus 1 quantity squared dx. Be careful squaring these, right? We're going to do them individually. I'm going to go ahead and pull the pi out of the integral as well. Still going from -2 to 1. We're going to FOIL this one out. So that's going to be x squared minus 6x plus 9. Foiling this one out and distributing the minus sign into it, we're going to have a -x to the 4th, a -2x squared, and a -1. So again, that was foiling it and distributing the minus sign. We can combine like terms now, still have the pi out in front. Looks like we have a -x to the 4th, which nothing will combine with that. Go ahead and cross it out since we're done with it. We have a couple of x squareds. Those will combine to be a -x squared. We have a -6x, which is by itself, and then we have a 9 and a -1, which is +8. Just to do the antiderivative of each of these, and we still have that pi sitting out in front. -x to the 4th is -1/5 x to the 5th. -x squared is -1/3 x cubed. -6x will go to -3x squared, and then 8 will go to 8x. And don't forget, we're plugging in our limits from -2 to 1. To try to do this real quick, in my head, I should have grabbed a calculator. I hope you guys have a calculator in front of you. If I plug 1 into all of this stuff, I'm just going to be adding all the coefficients together. So we have a -1/5, a -1/3, a -3, and a +8. And then we're going to subtract, plugging -2 into all of this. -2 to the 5th is -32, which cancels out with that negative. So that's going to be +32/5. 2 into there is going to be a -8, which again cancels out with the negatives. So that's a +8/3. -2 into here is a +4, so -12. -2 times that 8 is going to be a -16. All right, I'm going to pause the video here and then get the calculator. Okay, I walked like all the way downstairs to go find a calculator, and then I remembered, hey, I have the book opened up. Why even bother? So let me just go to the book. Here's our answer here, 117 pi over 5 after plugging all that stuff into the calculator. I also realized while looking at the book that I graphed it wrong, because I'm silly. I didn't graph a negative slope there, I graphed a positive slope. But look, even if you graph things wrong, you still get the right answer. So that was my bad. Let me just fix that, I guess. Shouldn't be like that. Should be like that instead. That looks a lot better for it being -2 and +1, that's for sure. So sorry about the graph. Make sure you graph negative slopes and not positive slopes. But look, math works out anyway. So good, so that's the washer method. Just for a quick little summary of everything that we've done so far, we have these 3 different things here. For whatever reason, I cannot go down. Well, we'll just make it work. Okay, so we have the cross-sectional area. Whenever you are finding the volume using cross-sections, you just integrate over the formula of the cross-sections. We also have the disk method. The disk method is finding volumes whenever you have rotation. So if your area is bordering your axis of rotation, then it's just pi, the radius as a function of x squared. Now remember, this could also be a function of y if you were integrating vertically. I still can't go down here. we'll just have to do it on another page. Sorry about that. And then so finally the other one is the washer method. The washer method you want to use whenever your area is not bordering the axis of rotation, where you have that gap that creates the washers. In this case, the volume is still pi, and then it's going to be the outside radius squared minus the inside radius squared. These could also be functions of y if you were integrating vertically, so just kind of keep that in mind. You'll see an example like that on the homeworks, and if you have questions from that, just ask during one of those meetings. Okay, ending the video here, and now we are done